Assalamualaikum and hi to my students. Um, Welcome to another video lecture of proving techniques, proof techniques. And we start first with the introduction. Some of the terms that we need to know. We start with the terminology of the theorems. A theorem is just a statement that can be shown to be true or false. Proving, of course, consists of some arguments and also the conclusion. The proposition is a less important theorem. Okay, read it on your own. Lemma, you will not find lemma in this course. Lemma is another theorem that is used to support the arguments to prove another theorem. Okay. Corollary is a byproduct. Sometimes in the proving, you will find another new theorem that can be produced. You will also not find any corollary in this course, except if you are a pure mathematician student. Pure math student will find these many things, like me. Conjecture is a statement that is proposed to be true, but it is unproven yet. If you have a statement which cannot be proven up until now, it is known as a conjecture. Some fact that I want to share to you is that in the field of mathematics, there is a known problem. There are many conjectures, but there are 7 millennium problems highlighted by Clay Institute of Mathematics. I don't remember when they proposed that. 7 millennium problem, which means it is a very important problem in mathematics, such that if you manage to prove the conjectures, you will get 1 million USD. And based on my knowledge right now, the problem, the reward is still there. So if you want to be 1 million USD richer, solve one of the Millennium Prize problem. Interestingly, from 7 of the Millennium Prize problem, 1 has already been solved by a Russian mathematician known as Gregory Perelman, where he solved the Poincare conjecture, and he refused the money as he says he's doing it for science. I want that money, but unfortunately I'm not that smart as compared to Gregory Perelman. In this topic of proof techniques, you will learn many various examples. You will actually prove many mathematical statements and hope that we can use it to extend your knowledge of proving to anything else, not only to mathematics, in any parts of your argument. Okay, we proceed right now with the definition, okay, of odd and even. From the previous lecture, I said that I will try to, as every chapters have some proving parts, and I want to relate it to the context of each chapter back. So next videos will come, consists of number theory, set relation and function, logic. I think we already covered the proving part very extensively, and lastly is the abstract algebra. But I don't really incorporate proof so much during chapter 1 and chapter 2, so I will revisit it again. We start first with the simple proof. This is still a number theory, but a more easier number theory part, which is the proving of even and odd. For example, if I have this statement, I start with the statement first, this one. Suppose that I need to prove that if an integer is even, then x squared is even. This is an implication. If, then. If x is even, then the implication is that x squared will also be even. Can we prove this? We start first with the definition. It's very important. Like my previous preparatory lecture said that if for every, okay, although this statement does not show every, actually it included in the statement, every x, if every x is even, then x squared is even. So you need to put your proof in a general statement. And to put a general statement, we start first with a definition. We cannot say, we cannot prove like this. This is a wrong proof. Don't do this. Some of my students actually did this. Let x is 6 because you know that 6 is even. 6 squared, x squared equals to 36, also even. And then as conclusion you say proven. And this is wrong according to the table from the previous lecture. You show an example, and to relate it, this is not a true, because it states that for every even integer, x squared should also be even. And this is a wrong way to prove when you only show one example. To show for all, you must show for every cases of even integer it will be true. So to start that, we need to generalize our term. For example, what is even number anyway? And if I ask this to you face to face, most of you say, I know even numbers. Even numbers is 2, 0, 4, 6, 8, 100, also even, 1000 also even. That is not a really good way to generalize your statement, because I might ask you back, what happens to -2? Is it even? 0, is it even? And then you start saying, yeah, it's even. A general term is much more easier. Actually, when it's defined here, an even number is just a multiple of 2. So 2 is a multiple of 2, 4 is a multiple of 2, 100 is also a multiple of 2. So basically an even number is a multiple of 2. According to this slide, it states that there exists k if n is even. There exists an integer such that n equals to 2k. So that is a multiple of 2. Let me use that example back. Even, if the number is even, then the definition is given as there exists a k is a integer, n equals to 2k. Seems familiar. This is from chapter 1. If a is a factor of b, then b equals to a times c. C is an integer from the first chapter. And also for the odd number, there exists k, which is an integer, but the difference in odd number right now is that it will be 2k plus 1. You might also find in some example it says that it is 2k minus 1, also happens to be true. It also happens that it will be an odd integer as well. So odd number can be 2k plus minus 1. So let's stick with this one first. Sorry. So it's established is that we must have the definition first. Then it will help us to prove the top statement. Okay, we start first with the direct method. If you remember modus ponens, then you know that it is actually a direct method. P implies Q. You show P and your conclusion is Q. The another one is modus tollens. Later we will explain those. Suppose you have this statement. Show that if x is even, then x squared is even. The idea is that, the proof, my idea should be like this. I start first with the definition of even, which is 2k. Therefore, I let n equals to 2k. K is an integer. That is for n. Oh, no, 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 no. The original question is x is even. I put this column as definition. Okay. The original pullback. X is even, therefore x equals to 2k, and k is a integer. So what will be your x squared? X squared is 2k squared. Right now, x squared does not really look like a multiple of 2 yet. If you extend it, if you expand it, it will be 4k squared. 4k squared is a multiple of 4. Our idea right now is trying to convince the audience is that it's actually is a multiple of 2 also. Therefore, I factorize it. This is an important part, 2k squared. This 2k squared, as k is an integer, k squared will also be an integer. K squared times 2, 2k squared is also an integer. Right? If you have that thinking, if you convince that if k is an integer, k squared is also integer, 2k squared is obviously an integer, you can put this 2k squared as something else. Let's name it as L. This L is 2k squared. And just now I said this L is also an integer. As x equals to 2k, x squared can be made as 2l, also a multiple of 2. X squared is also an even number. As my conclusion, this is true. I already proved to you if x is even, which is 2k, it's a multiple of 2, x squared is even, as shown by 2l. And your proof is complete. It's true, it's optional. It's optional. Most of your questions actually is already true. You need just to prove it. I think it's very seldom for us, for DMA lecturers, to prove it's false, otherwise it's shown to be false. But for this chapter, assume it's true first, because we want to make sure that the students can show the actual proof to be true. Okay, let's try to do this example. The example is that you need to prove x is odd, then x squared is odd. This time you should use the definition of an odd integer. Your proof might be like this. You let x equals to 2k plus 1. Again, k is an integer. You do all the x squared part, which is 2k plus 1 squared. Expand those. It will be 4k squared plus 4k plus 1. Then, based on our previous experience, that we should try to factorize 2. Factorize 2 for this case will happen to be like this. 1. How to factorize 1? You actually cannot factorize 1, right? And for this case, 1 is actually being put outside. And as k is an integer, again from the previous example, 2k squared plus 2k will also be just another integer. What is L? L is 2k squared plus 2k. This L is also an integer. Therefore, I just show to you that as x equals to 2k plus 1, then x squared can be made as a 2l plus 1. Don't forget to put the conclusion. It's proven that if x is odd, the implication x squared is odd as well. Let's try another example which is not in the slide. Suppose I have a claim, proof if x is even, still in the even and odd cases, and y is odd. I claim that the implication that then x plus y is odd. Sometimes it's very good if you manage to visualize the correct example in your head first, but that will not be your solution. My idea, the tips for you guys is that sometimes it's good to visualize the problem like this. Again, this is not a proof, and this is not wrong anyway. X equals to 6 is even. I let y equals to 7 is odd, and the summation of x and y will be odd because x plus y is 13. 13 is also odd. You should try to visualize first if you cannot do this directly. This happens to be a true statement, but again, we cannot use this as your proof because this is a proof by example which is not true for the case of for every. Why not we use this approach? The proof starts now. I let x equals to 2k and y equals to 2k plus 1, and I just do x plus y, which happens to be 2k. Okay. Sometimes a good practice is that I don't like to put the same k. I put 2l plus 1. Later I will explain in the next example why I happens to choose different integer. K is an integer, L is an integer. X plus y will be 2k plus 2l plus 1. Again, I try to factorize 2, becomes k plus l plus 1. K is an integer, L is an integer, k plus l will be another integer, 2m plus 1. M equals to k plus l. Therefore, if x is even and y is odd, x plus y will be 2m plus 1, which is odd. It's proven in a general statement. Proven if x is even, y is odd, x plus y is odd. Very easy. Okay, why not we choose try to do this example? Suppose I have a claim is that we prove the product is multiply product of two even integers will be even. Different way of representing a question. There is no if then. We start with the visualization. What this statement actually tell us about? What is the statement that should be proved? It states that the multiplication between two even will always be even. You can try to attempt those. You can try to take 2 times 2, yeah, 4. 4, even. 2 times 4, even, 8. 8 is also even. You can do that. I would directly go to the actual proof. I let x equals to 2k and another even integer, namely let's say y. This time, what happens if I put 2k here? If I manage to prove that the product xy will be even, actually if you use the same k, you just prove that the product of two same even will be even. If your k is the same, x equals to 2k, y equals to 2k, you just prove that two same even integers will be even. That's why from the previous example I said I don't like to put in the same k. You should assign it to a different integer, namely L, for example, because it will be more thorough. You will cover the same even integers on different even integers. L is integer. Okay. Next, I multiply x and y becomes 2k times 2l becomes 4kl. I factorize it into 2kl. As k is an integer, again the same argument, l is integer, the 2 times k times l will just be another integer. I define it m equals to 2kl and m is a integer. As my conclusion is that it's proven that if x is even, y is even, then the product between x and y will indeed be even. Don't forget to put the conclusion in full. Proven, product, blah blah blah. You just repeat it back. This is actually important. Sometimes it's just not about the repetition. Again, in your course, it's always true. But maybe if you are a mathematics student, pure mathematics student, sometimes the statement might be false. Conclusion is like a conclusion that ends the story. Proven that product of two even is even. Now the proof is complete. Your argument is there, definition, you do the arithmetic operation, you finish with a conclusion. That's complete the proof. That's all for no. I think I should include one more, but maybe we meet at the video lecture. I just want to highlight this example. You read this on your own and try to understand first. The question is that prove if the A and B are both perfect square. This time is not even and odd anymore. So you cannot use the definition of even and odd. You should use the definition of perfect square. So if you don't know the concept of perfect square, then you cannot answer it. Perfect square, what is the definition? It is some integer which can be represented as x squared. That x squared is x squared. But that x is an integer. For example, 1 is a perfect square because 1 can be made as 1 squared. 1 is an integer. 2 is not a perfect square because 2 cannot be made as x squared such that x is an integer. We proceed to the next perfect square. 4 is a perfect square because 4 can be made as 2 squared. 2 is an integer, and so on and so forth. In general term, the perfect square is just you let some, in this case a equals to x squared. That x is an integer. and the idea will proceed the same as like the previous event and on, just the different definition. Until we meet again for the next subtopic, indirect method. Thank you.